Welcome. Now, let us look at something that will be useful. You may have done this in earlier classes, but it is good to know clearly what this really is and the basis for this. That is why we are doing it here. It is nothing but the phase rule for non-reacting systems. In this module we are considering only non-reacting systems, therefore we will consider phase rule for non-reacting systems here. Let us consider a system containing pi number of phases, gas, liquid, vapor, solid and so on and so forth. Let us say in general it contains pi phases, and we also saw it is just not limited to these phases. They could be two distinct liquid phases, there could be many distinct liquid phases, there could be many distinct solid phases. It is a little difficult to imagine different vapor phases, but certainly there could be different liquid phases and different solid phases. Therefore, let us say in general that the system contains pi phases, and let the components in each phase be C, and we are going to implicitly assume that each component is present in each of the phases, or each component is present in all the phases. If the number of components in each phase is C, we know that the mole fractions or the mass fractions need to add up to 1. For example, if the mole fraction is x1, x1 plus x2 plus x3 and so on till plus xn must equal 1. So, this automatically gives us a relationship to be satisfied between the concentrations of the C components in each phase. Therefore, the composition of the phase is specified by C minus 1 variables. Suppose there are 5 components, we need to know the concentrations of 4 components, and the last component we can always get by adding the mole fractions of these 5 and equating it to 1. Therefore, if we have 4, we can always find the 5th one. Therefore, the composition of a phase is specified by C minus 1 variables. In addition, the temperature and pressure need to be specified, because they are conditions of equilibrium. Equality of temperature and equality of pressure across phases are conditions that need to be satisfied for equilibrium, and therefore, the total number of variables that need to be completely that are needed to completely specify a phase is C minus 1 plus 2, that equals C plus 1. That is C minus 1 variables of composition we saw, plus 2 variables temperature and pressure. You add these two together, you add all these together, you get C plus 1. And we said that each of these components is present in all the phases, and the total number of phases is pi, and therefore, the total number of variables needed to specify the state of the system, but not its size of course, is pi phases times C plus 1 variables that are required to specify in each phase. Therefore, pi into C plus 1. If the various phases of the system are at equilibrium with each other, then the conditions of equilibrium can be applied. That equations phi 1 to phi 5, which is T alpha equals T beta and so on, P alpha equals P beta equals P gamma and so on, and the chemical potential of each component in each phase must be the same, or of each component in the phases must be the same. There are C equations for chemical potential, one for each of the C components that are present, that we saw. If we have we wrote mu1 alpha equals mu1 beta equals mu1 gamma, then mu2 alpha equals mu2 beta equals mu3 gamma, mu2 gamma and so on, mu3 alpha equals mu3 beta and so on. So, you have C such equations if you have C components. Therefore, we have C equations for chemical potential, one for each of the C components and one each for the temperature and pressure. T alpha equals T beta equals T gamma, P alpha equals P beta equals P gamma, and therefore, we have a total of C plus 2 equations, and each of those equations corresponds to pi minus 1 separate equations, because T alpha equals T beta is one equation, T alpha equals T gamma equals another equation, and so on and so forth. Therefore, each of those equations corresponds to pi minus 1 separate equations, and therefore, the number of equations between the variables is pi minus 1 separate equations into C plus 2 equations. Why did we do all this? It is because of this. We know that for a meaningful solution set, when you are trying to solve knowing some set of variables and we are trying to solve for the other set of variables that are unknown, for a meaningful solution set, the number of variables must be greater than or equal to the number of independent equations, otherwise we do not get a unique solution. Thus, pi into C plus 1, number of variables that we saw earlier, must be greater than pi minus 1 into C plus 2 equations for a general case. We have completely generalized this. We said pi phases and C components, and we got the number of variables as pi into C plus 1, we got the number of independent equations between them as pi minus 1 into C plus 2, and we are using the mathematical criterion that the number of variables must be greater than or equal to the number of independent equations between them if we need to solve them uniquely. Therefore, pi into C plus 1 must be greater than or equal to pi minus 1 into C plus 2. In other words, if you transpose this, C minus pi plus 2 must be greater than or equal to 0. You can do the transposition and indeed find that C minus pi plus 2 equals 0 or is greater than or equal to 0. We will call this equation 5.6. The left hand side of 5.6, which is this C minus pi plus 2, this can be interpreted as the number of independent variables that are needed to completely specify the system, or in other words, the number of degrees of freedom for a given system, and let us indicate the number of degrees of freedom by f, and therefore f is nothing but C, number of components, minus pi, the number of phases, plus 2. This is the number of variables that are needed to completely specify the system. Let us call this equation 5.7, and some of you would have already realized that this is indeed called the phase rule, and application of the phase rule tells us the number of independent variables that are required to completely specify the state of a system if the number of phases and components are known. And of course, we have assumed the equilibrium conditions. We have written the phase rule for pi phases in equilibrium with each other. To get more comfortable, let us do this example. Find the number of independent variables that are needed to completely specify the state of the following systems: a pure component in a single phase, that is the first system; a pure component that is present as a mixture of liquid and vapor. Please take about 10 minutes. We have done a few things till now in this particular class. Please take a few minutes, go back and see what we have done and see what you need to solve this particular example. Take about 10 minutes for that. I will come back and tell you the solution. Go ahead, please. Okay. This was a straightforward application of the phase rule, therefore, most of you would have gotten the solution already. The solution is as follows. We said the first system is a pure component, which means C is 1, single phase, which means pi is 1, and therefore, C minus pi plus 2, in this cancel, we get f equals 2, and therefore both temperature and pressure need to be explicitly known. F essentially implies the number of independent variables that are needed to fix the state of a particular system, and typically temperature and pressure can be taken to be those variables of choice. The temperature and pressure need to be explicitly known to completely specify the state of the system. The second example was if the system is a pure component with brain C equals 1 in two phases pi equals 2, then F equals C minus pi plus 2, and that turns out to be 1. In this case we just need one variable, say temperature or pressure, and that is the only thing that is needed to completely specify the state of the system. The temperature, what this also means, or another way of looking at this, is that the temperature can be freely chosen, but the pressure, or excuse me, the pressure can be freely chosen, but the temperature cannot be freely chosen. It has a definite value for a particular other variable. For example, if the temperature can be freely chosen, the pressure will have a definite value for the chosen temperature. If the pressure can be freely chosen, then the temperature will have a definite value for that chosen pressure. See you in the next class.